There's one final curiosity that I'd like to discuss before leaving our talk of alternating series. Um, and in that context, I would like to revisit the alternating harmonic series one more time. So let's go back again to our board and write down the first several terms of the alternating harmonic series. And we've said that this converges and that it converges to the natural log of 2. But now what I'd like you to do is think of your favorite number, any number at all. I'm going to pick, how about the number 7? All right, so I'm going to start writing down the positive terms in the alternating harmonic series. So I'll begin with 1, move on to a third, move on to a fifth, and want to recognize that because these are some of the terms of the harmonic series, every other term of the harmonic series, if I were to continue in this way, just listing the positive terms, eventually I'm going to get beyond any number that I like. In particular, eventually I'm going to get beyond the number, what did I pick, 7? So eventually, right, I don't know, I'm going to add on something large enough in order to get beyond 7. And so this will represent the first time that that this sum is beyond 7. So this is greater than 7, but without the 1 over big, it was still less than 7. And then what I'm going to do is tack on the first negative term, minus 1/2. Well, now I'm below 7. Why? Well, 1/2 is a bigger number than 1 over big is, and I just subtracted 1/2 off of, well, this partial sum. But since adding 1 over big was the first time that I passed 7, subtracting something bigger than 1 over big is going to put me below 7. So at that point, I'm going to start tacking on my positive terms again. So let's see, my next positive term is going to be 1 over big plus 2, right? The denominators are increasing by 2 each time whenever I'm looking at the positive terms. 1 over big plus 4, and so on, until eventually, again, these are terms of the harmonic series. I know that if I add enough of these together, I'm going to get as large as I like. In particular, eventually I'm going to get beyond 7 again. And so 1 over bigger represents the first time that I got, again, beyond 7. At that point, I'm going to tack on the next negative term. And I'm going to continue this. Well, what's going to happen? So now, right, 1 over bigger plus 2, and so on, until I get beyond 7 one more time. So 1 over bigger still. And at which point I'm going to tack on the next negative term. Now, I'm going to continue this process infinitely often. So I'm going to have all of the terms of the alternating harmonic series that I had before, except I'm going to have them out of order. Well, what's this going to converge to? Well, let's see. By the time I tacked on 1 over big, I was just a little beyond 7, right? I was less than 1 over big, beyond 7, subtracted off 1/2. By the time I got to 1 over bigger, I was just beyond 7 again, but only just barely. I was much closer to it than I was at 1 over big. and then I subtracted off a fourth. All right. And so now 7 is tucked in here someplace. By the time I get to here, I'm really close to 7, just a little bit beyond, and I'm going to subtract off a sixth. 7 is somewhere in here someplace. And so I'm less than 1/6 of away from 7 at this point. I was less than 1/4 away from 7 at that point. Eventually, right, I'm gonna be at 1 over really super big. And then I'm going to subtract off. I don't know what this is going to turn out to be, a big even number. And so 7 is now trapped in here, but I'm less than this distance away from 7 at this point. So what we can see is that whenever I rearrange the terms this way, this thing is converging to 7. Replace the argument using whatever your favorite number happened to be, and you can make the terms of this series by rearranging them, form a new series that converges to something, whatever you like at all. And this is an interesting curiosity that happens because, well, let's see what made that happen. It was the fact that whenever I added the positive terms together, I could get as large as I liked. I could have actually picked as my favorite number something negative and began by using the negative terms and then tacking on a positive. I could have converged then to my favorite negative number. So this happens because the corresponding series with all positive terms, in our case, the harmonic series, diverges. And so in general, we have the following fact. So suppose that I've got a series that converges, but if I ignored the sign of the terms, right? So up here, I had negative numbers, but if I ignored the sign of the terms, then I wound up with a series that diverges. So if I ignore the signs, and I can do that by looking at the new series I get, whose terms are the absolute values of the terms of the series that I started with. If that series diverges, then the terms of my original series can be rearranged to converge to whatever number I wish. And so such a series that converges, but for which the absolute values of the terms form a series that diverges, that's called a conditionally convergent series. Oops, missed an N there. A conditionally convergent series is a series that converges but for which the series I get by looking at the absolute values of the terms of the original does not. And the conditional here, I like to think of that as meaning that the number to which the series converges is conditional on the arrangement of the terms. As another related definition, if the absolute values of the terms of a series converges, we say that the series without the absolute values is absolutely convergent. And here, right, this doesn't mean it really, really, really converges. That's not what the absolute means. The absolute is referring to the absolute value symbols, right? So if we have a series and we can build a new series by looking at the absolute values of the terms of the original series, if that new series converges, then we say that the original series is absolutely convergent. It's also important to note that if a series is absolutely convergent, it also is convergent. So that can be proven. We're not going to do that, but list that as a note. And that's actually a very handy theorem because sometimes it's easier, if we want to know whether or not a series converges, it's sometimes easier to ignore the signs, turn everything positive, and ask whether or not the new series converges. Now, this doesn't go in the other direction, right? If this converges, so does this, but this converging does not guarantee that that's going to converge. And the obvious counterexample to that is right up here, right? This series converges, but if I looked at the absolute values of the terms, I get a divergent series. So this statement only goes in one direction, but it can be very useful. All right, so that's our discussion about conditionally convergent and absolutely convergent series. Hope you enjoyed it.